Hooke's law states that the displacement and the resultant force, they have direct proportion to each other. So if you have got a spring and then you try to stretch the spring, okay, so we have got what we call the equilibrium position. At equilibrium position, the x value is 0. When I talk about x, when I'm talking about x, I'm talking about the displacement. Okay, now this resultant force which we're talking about here, or let me say Hooke's law, this is the formula for Hooke's law. Negative kx, where F is the resultant force, k is the spring constant, x is the displacement. Okay, so if you have got a spring and then you are trying to compress or you are trying to compress or you are trying to stretch the spring, there's what we call the original position or the equilibrium position, where the spring was before you compress or before you stretch. That is the equilibrium position. At that particular position, the x value is 0. Okay, now when you are trying to stretch the spring, you are going to use the force. Now that force you use is what we are going to call the applied force. But there is a force that is trying to bring the spring back to its equilibrium position. That is what we call the resultant force. Okay, so this is the resultant force. That is why we have got a negative in the equation. So as you can see, if the force increases, meaning the x has to go up. Now k is just basically the spring constant, and its SI unit is just basically Newton meter. Okay, Newton meter. So now k, it just basically tells you how loose or how stiff the spring is. If the k value is greater, meaning we are dealing with the stiff spring. If the k value is less, then meaning we are dealing with the loose spring. Okay, that is the only concept which you need to understand under Hooke's law. Okay, so let's say we have been given a spring and we have been told that this is the equilibrium position. Okay, now we are saying that at equilibrium position x is always 0, meaning even the resultant force at that particular point is 0. So let's say that you try to compress or you try to stretch the spring up to all the way to the displacement where we are going to have maybe 2 centimeters. Okay, and let's say that the spring constant you have been given that k is equal to 9.7 times 10 raised to the power 2 Newton per meter. Now let's find the resultant force. Okay, so the resultant force is going to be equal to negative kx. So we are going to plug in the values. We are going to have the negative is going to be 9.7 times 10 raised to the power 2 times this displacement is 2 centimeters, but you're supposed to convert it into meters. So converting from centimeters into meters, we need just to divide it by 100. So dividing 2 by 100, we're going to get 0.02. Okay, now if we do 9.7 times 10 raised to the power 2 times 0.02, I'm getting negative 19.4 newtons. Now what I want us to understand is that we are getting the magnitude of the resultant force. So we are going just to get to say the resultant force in this case is going to be 19.4 newtons. Okay, so we ignore the negative when reporting the answer. Okay, so you can find this is the relationship which is there between the resultant force and the displacement. The inverse proportion to each other. The moment when the resultant force increases, the displacement has to go up. When the displacement goes down, the resultant force has to go down as well. Okay. So let's get to understand what Young's modulus is. So when we're talking about Young's modulus, we're talking about the ratio between the stress and strain. Okay. So in some books, Young's modulus is represented by the symbol Y. Sometimes you are going to see Young's modulus is represented by symbol E. That is the same. So now in this video, we are going to use Young's modulus with the symbol Y. Okay. So we are saying that Young's modulus is the ratio between the stress divided by strain. Okay. So now when we're talking about stress, what are we talking about? When we're talking about stress, we are talking about the force divided by area. So again, stress is the ratio between the force and the area. So stress is also known as for pressure. Okay. Then whenever we're talking about strain, strain is the change in L divided by L initial. This change in L is just basically the change in length. So let's say we have a wire. So here is our wire. So we have the first part. So this one we are going to call it from there all the way to there. We are going to call it as L initial. Okay. Then we apply a force. We are trying to increase the length, or we are trying to stretch the wire. So this is what is going to happen. The wire will be somewhere there. Okay. So this now, the length from here all the way to down there, that is the L final. So the length from this point all the way to this point, this is our change in L. Okay. So strain, it just gives us the ratio between the change in L divided by the L initial. So we can say that change in L is just basically L final minus L initial. Okay. So when we're talking about strain, just think of this example which I've just explained here. Now, we are talking about Young's modulus, remember? So let's talk more about this Young's modulus. So this Young's modulus, it gives us the property of a material. It can give us the property of any material in terms of when you stretch the material or you compress the material. Now what it means there is that if the Young's modulus is greater, meaning you are dealing with stiff material, when the Young's modulus is loose, or let me say less, the value is less, you are dealing with what? Loose material. Okay, let's think of the wire. If the Young's modulus, the value is maybe greater, then we are dealing with a stiff material. That wire is stiff. Okay. Now, since we are saying that stress is force divided by area, okay, we are saying that it is force divided by area. Then stress, it is change in L divided by L initial. So we can say that Young's modulus, this is the same as we say we have this, then you have this. So at the same time, this will be like this times this, then change in L. Now, this change in L, it is the same as, we can say it is the same as compression. It is also the same as extension. Sometimes they can ask you to find extension, or they can ask you to find compression, meaning they're asking you to find the change in L, okay, the change in length. That is what we're talking about. So now this is going to give us Young's modulus. The formula will be now the force times the change in L divided by area times change in what? Change in L. So it is the Young's modulus is equal to the force times the initial length divided by area times the change in L. That is what I wanted you to understand. Now, let's say we have a question. For example, this is the question which you have. The question is saying a 15 centimeter long tendon was found to stretch 3.7 millimeters by a force of 13.4 newtons. The tendon was approximately round with an average, this is supposed to be found, it was found with an average diameter of 8.5 millimeters. Calculate the Young's modulus of this tendon. Okay, that 5 is not supposed to be there, it's supposed to be of this tendon. Now, what we need to understand is that we are saying this is supposed to be found, 5 is not supposed to be here. Okay, so we know that Young's modulus, we are saying that it is the force times change in L times L initial divided by area times change in what? Change in L. So from the data which we have, we can see that we have the force. We have the force as 13 0.4 Newton. We have the L initial. The L initial, we can see that it is 15 centimeters, but we can change this into meters, which is going to be 15 divided by 100, which is going to be 0. What? 0.15 meters. Then it was found to stretch. This is the change in L. Okay, change in L, which is 3.7 millimeters. So this 3.7, to convert it into meters, I'm supposed to divide it. First, I can convert it into centimeters. I'm going to divide it by 10. And then meaning I've converted from millimeters into centimeters. Again, converting from centimeters to meters, we divide it by 100, which is just the same as dividing it by a 1000. Okay, so I'm going to divide it by a 1000, which is going to give me 0.0037 meters. Now we need to find the area. We know that area, since we have been given the diameter, the tendon, if this is the tendon, let's say this is our tendon. Okay, so it has got the diameter, meaning that the area of the tendon is going to be pi r squared. Okay, so pi, then the radius is the same. So this is the diameter. We need to change this one to have, so to get the diameter, we're going to say 8.5 divided by 2. That will be our diameter. It is 4.25. So our radius now is going to be 4.25 centimeters or millimeters. So converting this one into meters, I need to divide it by 1000, which is going to give me as in 0.00425. Now I have to square it. So I'm going to say that pi times 0.00425, then I square it. So I can just put this in scientific notation, which is going to give me a 5.675 times 10 raised to the power negative 5 meter squared. So now I'm going to get rid of this. Okay, I can now plug in the values. Okay, so we are saying that the Young's modulus is going to be, the force is 13.4 times the L initial is 0.15, everything divided by area is 5.675 times 10 raised to the power negative 5. Okay, then times the change in L is 0.037. Okay, so what will be our Young's modulus? So we have on top 13.4 times 0.15, then I divide this by 5. I'm going to open the brackets, 5.675 exponent negative 5, then times 0.0037. Okay, so this is giving me a 9.57. So what we're going to do is we check here. This is in one decimal place, so even our answer is supposed to be in one decimal place. But first I can put this, and then I say times 10 raised to the power 6. Now, what are the SI units for Young's modulus? Remember that we have this. This is going to give us meters. This is going to give us meters. Okay? So if this is going to give us meters, this is going to give us meters, meaning these two, they are going to cancel. So we are going to have Newton per square meter. Okay, so it's going to be Newton per square meter. So that is our answer. So now to simplify this, we can say that our Young's modulus is 9.6 times 10 raised to the power 6 Newton per square meter. So this is the answer for this question. Now let's get to see how we can answer this question, the next question we should have. The question is saying a bone has Young's modulus of 18 is 18 times 10 raised to the power 9 pascals. Under compression, it can withstand a stress of about 160 times 10 raised to the power 6 pascals before breaking. Okay, assume that the femur is 0.5 meters long and calculate the amount of compression this bone can withstand before breaking. I explained to say whenever they're asking about the compression, what is the amount of compression, or they ask about extension, they're asking about the change in L. Okay, so we're going to say that Young's modulus, it is the force times L initial, then area times change in L. So they want us to find the change in L. So we can make change in L as a subject of formula, which is going to be Young's modulus times area times change in L is going to be force. Then you have this. Okay. What else do we have? So we are going to have we are going to divide both sides by Young's modulus and area. Even here, Young's modulus and the area. So these they will cancel. So I'm going to remain with the change in L is going to be equal to the force times change in L. Then we have the area times the Young's modulus. But remember, the question is saying we have the stress. Remember, stress is given by force divided by area. Okay, so now if we know that this part here, it can give us stress, so we can say that this change in L now is going to be change in L is going to be equal to the stress. Since force over area is stress, then we are going to have this is going to be the change in L, or the L initial divided by what? The Young's modulus. So we can now plug in the values. We have this. The stress, we have been told that it is 160. Okay, 160 times 10 raised to the power 6. Then we need to do times, or we can put this in brackets. We have times, then the L initial is we have been told that it is 0.50 meters. Okay, divided by the Young's modulus. The Young's modulus is 18 times 10 raised to the power 9. Now what we need to understand here is this: Young's modulus and stress, they are having the same SI units. So these SI units are going to cancel. They are going to cancel out. So we are going to remain with meters, and we want our answer to be in meters. Okay. So what we are going to do now is we are going to find the answer. So change in L will be equal to, we are going to have 160 exponent 6 times 0.5. The answer I get divided by 18 exponent 9. Okay, so the answer I'm getting is 4.44 times 10 raised to the power negative 3 meters. So that is the amount of compression this bone can withstand before breaking. So you can convert this. This one is the same as 0. You can say 0.0044 meters. So that is it. This is what you're supposed to know under Young's modulus. So let's talk about the elastic and potential energy. We are still talking about simple harmonic motion. This is one of the subtopic which is under simple harmonic motion. Now we know that whenever we're talking about the simple harmonic motion, we are talking about the spring. Okay, so now whenever you are compressing the spring, there is energy which is being stored. Okay, so let's say we have the spring. Here is our spring. So whenever I'm trying to stretch this spring, there is energy which is being stored. Now that energy is what we call the elastic potential energy. Okay, quite okay. We know that once we release the spring from rest, this spring will go to the equilibrium position, and then it compresses, it goes back to its original position. Then we can see that we are going to have the velocity. So in that case, we can also say that since we're talking about energy, meaning we have also the kinetic energy. Okay, so elastic potential energy is given by half kx squared. Okay, so the elastic potential energy which is being stored in the spring is also known as the work done by the spring. Okay, so why are we saying that the elastic potential energy, the energy which is being stored, or the elastic potential energy which is being stored in a spring, is also known as the work done by the spring? Because we know that if we have our spring, we're saying that this is our spring. So let's say we have the mass, then this is our equilibrium position. Okay, so we know that from here, if we have stretched this one all the way to this point, we are going to have the x. So we know that we have the force. Okay, we have the restorant force. This is the applied force, and the restorant force is in opposite direction to the what? The applied force. So we know that force is equal to, or let's say we have the force and the displacement. So work is given by the force times the displacement. So in this case, the displacement is the x. That's why we are saying that the elastic potential energy is also known as, is the same as what? The work done by the spring. Okay, that is very, 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 very important. Now, let's talk about the conservation of energy. Remember, we have kinetic energy, potential energy. Now we have two types of potential energy. We have what we call the elastic potential energy and gravitational potential energy. Now, gravitational potential energy, in this case, we are not going to consider it because we don't have, uh, the spring is not under the influence of gravity. Okay, but once the spring is under the influence of gravity, sometimes they can ask you to find the gravitational potential energy. Okay, so what we are going to do now is this. Okay, the conservation of energy which we are talking about, we know that we are going to start with the mechanical energy. Mechanical energy is just the sum of all the energy which we have, or all the energy which are being stored in the spring. That is the mechanical energy. So in this case, we are talking about three types of energy. We're talking about the elastic potential energy, the kinetic energy, and the gravitational potential energy. But we are saying the gravitational potential energy, we're not going to consider it, meaning we're going to have two types of energy: the elastic potential energy and the kinetic energy. Okay, so now we're going to say that the mechanical energy is going to be equal to the sum of all the potential, elastic potential energy, plus the kinetic energy. Now the mechanical energy is given by the formula half ka squared, where a is the amplitude. Amplitude is the same as the x, but whenever we're talking about the amplitude, meaning you have stretched, you have reached at its maximum position, that is the a. Okay, so the elastic potential energy, we have said that it is half kx squared. Then the kinetic energy, we know that is half mv squared. Now, before we come up with some certain formulas, I want us to talk more about the spring. Okay, so now let's say we have a spring. This is our spring. We are trying to stretch this spring. Okay, so here is our spring. So we have the mass. Let's say that at this point, this is our equilibrium position. So at equilibrium position, what we need to understand is that x is always 0. So according to the formula where we are saying restorant force is equal to negative kx, if x is 0, we expect our restorant force to be also 0. Okay, at the same time, we need to know that at this point, that's where we are going to have the maximum velocity. When x is equal to 0, we are going to have the maximum velocity. So if we have the maximum velocity, we know that we are going to have maximum kinetic energy. Okay, at the same time, if x is 0, we don't expect to have potential energy. So at this point, potential energy is going to be 0. That is very, very important. Now, the moment when we reach at maximum position, we are stretching this, then we have reached at maximum position. What we need to know is that at this point, the spring is not moving, meaning that the velocity is going to be 0. We are going to have the maximum acceleration. Okay, so the x is going to be equal to, is going to be a. Okay, now at this point, we expect to have the maximum potential energy because we are going to have x. We don't expect to have the kinetic energy. So the kinetic energy at this point is going to be 0. Okay, now when you're trying to compress this is the same thing which we're going to have. Okay, so if I'm trying to compress here, we're going to see that we're going to have the maximum acceleration, the kinetic energy is going to be 0, the velocity will be 0, then we are going to have uh, the potential energy is going to be at its maximum position. Now when the spring is at equilibrium, what we need to understand is that meaning we are going to have the maximum velocity. So whenever they are trying to ask you to find the maximum velocity, just know that we are talking about when the spring is at equilibrium. Okay, so when the spring is at equilibrium, x is equal to 0. That is very, very important, guys. Now what we need to know is that if x is equal to 0, we don't expect to have potential energy, meaning that at that point, if we don't have potential energy, meaning that we are going to have the maximum velocity. So we can find the formula which is going to help us to find the maximum velocity when x is equal to 0. So when the spring is at equilibrium, x is equal to 0, we are going to have the maximum velocity. Okay, so if the maximum velocity, I don't expect to have this if x is equal to 0. So I'm going to have half ka squared is going to be equal to half mv squared. In short, what we are trying to say is the mechanical energy is going to be equal to the kinetic energy when x is equal to 0, or when you have reached at its maximum, when the velocity is at its maximum position. Now when the velocity is at its maximum position, x is equal to 0. Okay, so we are trying to make v as a subject of formula. Now this velocity which you are calculating now is when x is equal to 0. Okay, which is the maximum velocity. So to get rid of half, what I'm going to do times 2 everywhere. So this is going to give me ka squared is going to be equal to mv squared. I can divide both sides by m, I can divide both sides by m. Okay, so I'm going to have v squared is going to be equal to ka squared divided by m. I can get the square root both sides, even here. So this is going to plus or minus, but we can just put it as plus. That is just okay. Then the formula now is going to be v max is the maximum velocity, remember, is going to be equal to the square root of k a squared divided by m. Now this is the formula for finding the maximum velocity. Now sometimes in some other books you are going to see this formula written to be v max to be equal to the square root of k divided by m. Then we are going to put a to the outside the square root, meaning this squared is going to be eliminated. So this is the formula for what? Finding the maximum velocity when x is equal to 0, or when the spring is at equilibrium position. That is very, very important. Okay, now how do we tend to find the acceleration, the maximum acceleration? Okay, so to find the maximum acceleration, what we have to understand is that when you're talking about the maximum acceleration, the velocity is going to be equal to 0. Meaning, say the resultant force is negative kx. So according to Newton's second law, we know that force is equal to mass times acceleration. So what I'm going to do is I'm going to replace this with the mass times acceleration. So I'm going to replace it there. So it's going to be mass times acceleration is going to be equal to negative kx. But what we need to understand again is that this negative, if I want, I can ignore it, because this resultant force is also going to carry a negative. Okay, so this is going to be the same as ma is going to be equal to kx. So this is going to give us a will be equal to kx divided by what? Divided by m. So this formula, we can write it in this state. So this we're saying that whenever we're talking about the maximum acceleration, meaning that we're talking about you have stretched the spring and the spring has reached at its maximum position. So at maximum position, x is equal to a. So what I'm going to do now, where there is x, I'm going to replace with what? A. So the maximum acceleration is going to be k times a divided by m. So this formula, sometimes you are going to see it written as this. then we have K over M times A, just like this. So this is the formula which is going to help us to find the what? The maximum acceleration. Okay, that is very, very important. So now from elastic potential energy, we can now see that we can know we can solve any question involving the maximum velocity, the maximum acceleration, and so on. Now let's talk more about the formula for elastic potential energy. Okay, we need to talk more about that. So we said the formula for elastic potential energy is given by elastic potential energy is a half kx squared. Now we are saying that work is the same as the elastic potential energy because this is the energy which is being stored in the spring. Now we can say that work is going to be equal to half kx squared as well. But how can we show that the work done by the spring is given by this formula? Okay, that is also very, very important. So what we need to understand is that we know that from work energy theorem, or from work energy and power, we know that work is given by force times distance. But whenever we're talking about the spring, this displacement now is going to be x. If this is the equilibrium, all the way from this to this is going to be x. So work will be equal to the force times x. Now what we are going to do now, we are going to use integral method. We are going to integrate this function. So we are going to integrate in terms of what? In terms of x. So if I want to integrate this in terms of x, this is what we are going to get. It's going to be the integral of the force, okay, the force. Then since I'm integrating in terms of x, this x is going to be dx. Okay, now from here we also know that force is equal to kx. So I'm going to replace force with the kx. So work will be equal to the integral of kx dx. Now I can integrate this. I know that whenever we are trying to integrate something, let's say we have the integral of maybe 4x dx, this is going to give us 4x squared over 2 plus c, which is the same as 2x squared plus c. Okay, let's say we have just x. Okay, the integral of x dx, this is going to give us x squared over 2 plus c. That is very, very important. Now how can we integrate this? We're integrating this in terms of x. So what I am going to do is work will be equal to, this k is constant, I'm going to put it outside. K, the integral of x dx. So to integrate that one is going to be k, then we are going to have x squared over 2. Okay, so I'm not going to include the constant, which is just okay because we are trying just to come up with a formula. So this is the same as work will be equal to half kx squared. So this is how you can show that the work done by the spring is given by half kx squared. Okay, so let's talk about how to find the velocity at any point. Remember, this is part 2 of the previous video where we were talking about finding the maximum velocity, and we said that whenever we're trying to find the maximum velocity, x is equal to 0. Now let's assume to say we have the value of x. Okay, so let's say we have the spring. Here is our spring. Okay, so if this is our spring, we know that if this is our equilibrium position, x is going to be equal to 0 at this point. So let's say we are not finding the velocity when x was equal to 0, but we are finding the velocity at any point. It might be this point, or anywhere. Okay, now whenever we're trying to find the velocity at any point, meaning that we have the x value, so from the mechanical energy or from the conservation of energy, we came up with a certain formula. If you managed to watch the previous video, we said the mechanical energy is equal to the kinetic energy plus the elastic potential energy. Then we say that the mechanical energy is half Ka squared plus has to be equal to and not plus. This is equal to, the kinetic energy is half mv squared plus the elastic potential energy is half kx squared. Now, we're not going to cancel anything because we are finding the velocity at any point. Okay? So, we are trying to come up with the formula which is going to help us to find the velocity at any point. So, where we have the value of x, how do we find the velocity? So now we have half ka squared is equal to half mv squared plus half kx squared. Okay, so now I'll get rid of this to create space. Then I'm going to do times 2 everywhere. Why am I doing this? I'm trying to eliminate the half. Okay, so 2 times everything inside here, the 2 and the 2 down here, they are going to cancel. So we're going to have ka squared is going to be equal to, here we're going to have mv squared plus here we're going to have kx squared. Okay, what else? We are trying to find the velocity. I'm going to shift kx squared to the left hand side. So it's going to be ka squared minus kx squared is going to be equal to mv squared. Now I can divide both sides by m. Here I will divide by m. So I'm going to have v squared. What I can do, I can factor out k. So k will be open brackets a squared minus x squared, then everything divided by what? By m. Okay, so we can get the square root to both sides for us to make v as a subject of formula. Okay, so this is going to give us v squared, we have k open brackets a squared minus x squared, and we have m. What I can do now from here, I can get the square root to both sides. If I get the square root to this side, also I get the square root to this side, this is what we're going to have. We're going to have the velocity at any point, which is going to be equal to k open brackets a squared minus x squared, everything divided by m. Now everything here is in the square root, but you can leave it here to say this is the formula, but you also know that this, you can shift this to the outside the what? The square root. So this is going to be the same as v is going to be equal to the root of k over m times a minus x. Now when I do this, meaning I've removed the what? The square root. But sometimes this one can confuse you. What you can just do is you can just leave it here. So this is going to be the final formula for finding the what? The velocity at any point. So at any given point, as long as you have the value of x, you also have the velocity. It's possible you can find the velocity using this formula. Okay. In this tutorial, we are going to talk about simple harmonic motion. Okay, so we want to talk about the position, the velocity, and the acceleration as a function of time. So we want to get the relationship which is there between the simple harmonic motion and the circular motion. Okay, now, if we talk about circular motion, we're talking about an object moving around the circle. Okay, so let's get to have our circle. Let's say this is our circle. Okay, now we want to find the equations which they are going to help us to find the displacement or the position. Okay, under simple harmonic motion, the position, the velocity, and the acceleration as a function of time. If I've been given a time, or if I've been given the time, how do we come up with the position? How do we come up with the velocity? How do we come up with the acceleration? Okay, so now if you have got a circle, an object is moving around the circle, we know that we can have I want us to have the xy plane, and then what we need to understand from here is that we are going to have the radius from this point here all the way to this point. That will be my radius. Then we need to have this, then we have this. So now I want us to have the theta. We are going to have the angle which is going to be formed here, and then we know that since this is not the maximum position, is going to be our x. So the radius, when you talk of the radius under simple harmonic motion, under simple harmonic motion is the amplitude. So I'm going to put the amplitude here. We know that when the x reaches at the maximum position, that will be our amplitude. So this part here, I've put x because it has not reached to it has not touched the circle here. Okay, so meaning it is not at its maximum position. Now what I want us to do there is we need to come up with x. X is going to be the displacement, okay, as a function of time. So now we can use SOHCAHTOA to come up with what? The trig function which is going to help us to find the displacement. Okay, so from here we know that for us to find x, we can use what? We can use cos. We know that cos theta is going to be equal to, okay, it's the adjacent. The adjacent is x divided by what? The hypotenuse, which is a. So to solve for x is going to be equal to a cos theta. Now when something is moving around the circle, we're talking about the displacement or the position as a function of time. Okay, when an object is moving around the circle, then this formula is correct. Okay, we can say that d velocity is equal to the distance over time. But now when we come to circular motion, we know that when we're talking about the velocity, meaning we're talking about what? The angular what? The angular velocity. This displacement is the same as we're talking about the angular displacement. Then the time, we're still talking about the same time which we're talking about. Okay, time doesn't change. Now from there, what we need to understand is that from this formula which we have just come up with, I want us to make theta as a subject of formula. So to make theta as a subject of formula, we are going to see that theta is going to be equal to the w times t. So I want us to plug in this value where there is theta. So we're going to find that the x as a function of time is going to be given by this. Then where there is theta, I put this. So this happened to be our formula for finding the displacement as a function of time. But at the same time, we know that we are saying that our formula is let me first create space here. We are saying that the displacement as a function of time, or the position, is the same thing, is given by a, then we have cos wt. But at the same time, we know that this w is just basically the angular frequency, and remember that the angular frequency is given by 2 pi f. I can replace this with what I have, so I can say that this as a function of time, I'm going to have the amplitude cos then here I'm going to put where there's the angular frequency, I'm going to put this, then times time. Okay, so we can say that these two happen to be our formulas, which they're going to help us to find what the position as a function of time. Now to get the velocity as a function of time, we need just to get the derivative of this function. Okay, as long as we get the derivative of that function, then we are going to get the what? The formula which is going to help us to find the velocity. Now we know that when we are differentiating the trig, if I want to differentiate what is the derivative of cos theta, the derivative of cos theta is just basically negative sine theta. Okay, the derivative of sine theta is cos theta. Now what I want us to understand is that if we have been given a function which is cos maybe 2 theta, the derivative of this one is just basically, you just get the constant which have been given where there's theta. So it's going to be negative 2 sine, then you keep what is inside constant. Okay, now we are going to differentiate this function as a function of time, but we are going to be keeping time as constant, and then we are going to be differentiating what? We are going to be treating the angular frequency as a constant. Okay, so now what we are going to be doing there is I want us to work with this one. I want us to work with this formula. It's the one which we are going to be using. So we differentiate this one, we are going to get the velocity as a function of time. Okay, so to differentiate this one, we are going to keep these, we are going to treat them as what? We are going to treat this one as a constant. So we are going to say that we're going to only deal with this one. So we are supposed to say it's going to be negative a sine, then here I'm going to say w over t times t. Then I need to do to shift this guy to come outside again. So I'm going to have this. So this is going to be the same as v as a function of time is going to be equal to negative angular times a sine this. But at the same time, you can replace this part here inside where there's w with 2 pi f, which is going to give you v. Then we are going to have this. We're going to have 2 pi f times t, which is going to be another formula. So we have got this formula for velocity and this formula. Okay, now we can also come up with another formula for acceleration. The moment I differentiate the formula for velocity, is going to give me the acceleration. Okay, now from there, what I want us to understand is that it's going to give us, we are saying that the formula for velocity as a function of time is just basically negative wa sine this. So we're going to get this one. If we differentiate it, we are going to get the formula for acceleration as a function of time. So I'm going to have this. So the derivative of sine is just basically cos, and then I'm going to put what is here. But remember, we are supposed to do times what is out this part here. So I'm going to put w. So this w and this w is going to give us w squared, or omega squared. So I'm going to have this. It's going to give me this. Then I have this. So at the same time, I know that this is just basically this. I can replace this with that one. So I'm going to have this. Then I'm going to have a cos 2 pi f times t. So this is also the formula. So you can either use this or you can use this. They're all going to give us the same answers. Now, from there are also some other formulas which you need to be familiar with. Sometimes if you're going to be given more like a theta, okay, meaning you are supposed to use the one for displacement is going to be, we are going to be given what we call this. Okay, so if you have been given this symbol here, you have been given the value of that one, meaning the formula changes. The formula which you are supposed to use is going to come as it's going to be like this, then plus that one. Okay, so now sometimes they can give you, they are going to be giving you the value of this. They can give you pi over 3. Yeah, so you just plug in the values. But in most cases, you are going to be using just dialect the way it is. So these are the formulas which are they're going to be helping us to find the position, the velocity, and the acceleration as a function of time. Okay. In this tutorial, we are going to talk about the relationship between simple harmonic motion and circular motion. Okay, so if we have got an object moving around the circle, that is circular motion, and then we do know that we are going to have the radius. Okay, so if we have the radius, and then we also have the x, or yes, we say the x, the position, and then I want us to have, we know that when we're talking about the spring, the amplitude under a circular motion, the amplitude is the same as what? The radius. So this is our radius, but I want us to put, since we're talking about simple harmonic motion, we are going to put the amplitude as a. Okay, and then from there, I want us to put this part here is going to be the x, which is the position or the displacement. Now, what I want you to understand, again here is that when an object is moving around the circle, meaning there is what? Angular velocity. Okay? Now, another thing is that when an object is moving around the circle, then velocity is given by distance over time. Okay? But this distance which we're talking about here is just basically the arc length, which is the circumference of the circle, which is given by 2 pi r. Now, the time is going to take to move from this point all the way to A. That is the period. Okay, so we can say that the time which we're talking about there is just basically the period. So we can say that is the period. So we can say that V is going to be equal to, where there's d, we are going to put 2 by r, everything divided by what? Everything divided by the period. But now, we are talking about the r under simple harmonic motion, we're talking about the amplitude. So we're going to say that v is going to be equal to 2 by the amplitude divided by t. Now, we want to come up with the formula which is going to help us to find the period, the frequency, and the angular frequency. Okay? Now, from here, we know that we can make t, which is the period, as a subject of formula. So it's going to be t v is going to be equal to 2 pi a. We divide by v, even here by v, we are going to find that our period is going to be equal to, we are going to have period is going to be equal to 2 by amplitude divided by v. But now what we need to remember is that we talked about how to find the formula of the maximum velocity. Okay, and we came up with v max is given by what? Is given by the square root of k over m times the amplitude. Now, in this formula, I want us to make the amplitude as a subject of formula. Okay? Now, to make the amplitude as a subject of formula is the same as if I can just get the reciprocal of, I do times the reciprocal of what is in the square root. So I get this. Then this and this, they'll cancel. Then I'll say this times the velocity, I'm going to get v, the square root of what? The square root of m over k. Then is equal to amplitude. Now, what I want us to do now from here is that I want us to replace where there is a with v, the square root of m over k. Okay, so we have got the amplitude as v times the square root of m over k. So I want us to plug in this value. Okay, so we have t is going to be equal to, we have got 2 pi, then where there is a, we are going to put v times what? The square root of m over k. Okay, so t is going to be equal to, oh, here there is over what? There is over v. So we can see that this v and this v here, they can go. So we're going to have 2 pi the square root of m over k. So this happens to be our formula for finding period. Okay, now we know that frequency, to get the formula for frequency, we know that frequency is just the reciprocal of period. So frequency is given by half, is given 1 over the period. So we're going to say that it's going to be 1 divided by, we have got the period, which is 2 pi the square root of m over k. Now from there, what we are going to do is we're going to separate these. We're going to say this is going to be 1 over 2 pi times 1 over the square root of m over k. Now that part which we have here, let me just put this formula for period here. We have 2 pi the square root of m over k. Okay, so I want us to have I want us to now expand this. So we have got 1 over, that is the same as 1 over the square root, we have got the square root of m over k. So this is the same as 1 times the square root of k over m, which is going to be k over m, meaning that the formula for frequency is going to be 1 over 2 pi times the square root of k over m. Okay, so this will be our formula. It will be 1 over 2 pi the square root of k over m. So that is the formula for finding frequency. Now, we also know that when you are talking about an object moving around the circle, then we also have the formula which is now when you're talking about circular motion, when you see this symbol, we know that that is the angular velocity. But when we come to simple harmonic motion, this symbol is angular frequency. Okay, but we know that under circular motion we have got the formula which is the theta is divided by what? The time. Okay, under circular motion, that is the formula which we have. But now this theta, when you move the whole circle, is just basically 2 pi. Okay, so that 2 pi, we are going to put 2 pi where there is what? The theta. So I'm going to say that this is going to be given by 2 pi divided by what? The time which we're talking about here is just basically the what? The period. Okay, so it's going to be, if I put this one to be 2 pi times 1 over t, we know that 1 over t is just basically equal to frequency. So I can say that this is going to be equal to 2 pi times frequency. Okay, but now we also know that frequency is given by 1 over 2 pi times the square root of k over m. So I'm going to put where there is frequency in this formula with what? 1 over. So I'm going to say that this is going to be given by, we have got 2 pi times where there is frequency, I'm going to put this. Okay, I'm going to put 1 over 2 pi times the square root of what? K over m. So we can see that the 2 pi and 2 pi, they can cancel. So the formula for angular frequency is going to be equal to the square root of k over m. So this is the relationship which is there between the circular motion and the simple harmonic motion. So when it comes for simple harmonic motion, the angular frequency is given by the square root of k over m, then the period is given by the 2 pi, the square root of m over k, and the frequency is given by 1 over 2 pi times the square root of k over m. Okay. Okay, so we have a question, and Hooke's law. The question is saying a spring that obeys Hooke's law has a spring constant k. Show that the energy stored E in the spring when it has been extended elastically by an amount of x is given by work is equal to half kx squared. Okay, so now what we need to understand here is we know that work is force times distance, but whenever we're talking about the spring, this distance is the x. Okay, so what I'm going to do now is, where there is d, I'm going to replace with what? X. Okay, so I'll go there and say work will be equal to the force times in x. Now for me to find the formula which we use to calculate which we use to find the work, what I have to do is I need to get the integral. Okay, so I'm going to say that work will be equal to the integral over, so I'm going to integrate this in terms of x, meaning that it's going to be the force times the x. So I'm integrating it in terms of x. That's why where there's x, I've put what? The x, which is just the same thing. So from here now I know that force, according to Hooke's law, force is equal to k times x. So I'm going to say that work will be equal to the integral over kx dx. Now I want to integrate this. It's the same as if you have the integral of x dx, the answer is going to be x squared over 2 plus c. Okay, so now what if we have the integral of maybe 4x, okay, dx? So this is going to be 4x squared divided by 2 plus c, which is the same as 2x squared plus c. So now I'm integrating this in terms of x. What I'm going to have, we're going to have work will be equal to, if I integrate this one, I'm going to have the k is constant, so I'm going to say x is going to be to the power 2 divided by 2. So this is the same as work is equal to 1 over 2 kx squared. So this is how you can show that the work done, or the work or the energy stored in a spring, is given by this formula. Okay, that is it for this question. So we have the next question, which is saying a wire of length 1.7 meters hung vertically from a fixed point as shown in the figure below. The wire has a cross-section area of 5.74 times 10 raised to the power negative 8 square meters and is made of a material that has a Young's modulus of 1.6 times 10 raised to the power 11 pascals. A load of 25 Newton is hung from the wire. Part 1, calculate the extension of the wire. Part 2, the same load is hung from a second wire of the same material. This wire is twice the length but the same volume as the first wire. State and explain how the extension of the second wire compares with that of the first one. Okay, so now the first question is talking about the Young's modulus. So now allow me to explain first what Young's modulus is. Okay, so Young's modulus, this is the relationship between the stress and strain. So in simple words, we can just say that Young's modulus represented by the letter Y. In some books, you are going to see Young's modulus represented by symbol letter E. Okay, so now in this video, I'm going to use Young's modulus as Y. So I'm going to say that Young's modulus is given by stress divided by strain. Now, whenever we're talking about stress, stress is just the relationship between the force and the area. So it is the force per unit area. So it is force divided by area. Then whenever we're talking about strain, this is the change in L divided by L initial. That is the extension divided by the original length. The change in L is the extension. So whenever they ask about extension, we are talking about the change in L. Okay. So now I can derive the formula here where I can say the Young's modulus is going to be equal to stress. We are saying that it is force divided by area. Then you have this. Then strain is a change in L divided by what? L initial. So this is the same as the force divided by area divided by, we have change in L divided by L initial. Okay, so I can say this is going to give me L initial, then here I'm going to have this. So to make things simple, we can say that Young's modulus is equal to the force times L initial divided by change in L, okay, times area. So now the question is asking us to find the extension. Remember I said extension is the change in L. Okay, change in L, let's say we have a wire. Okay, here is our first wire. Now the original length, we say this is the original length from here all the way to there, that is L initial. Now the same wire, if we apply a force, this wire is going to be extended to some amount of length somewhere here. Okay, so now what is happening here is that this is the L final from there all the way to there, that is L final. So the change in L is this part here from there all the way to this point, that is the change in L. Okay, so change in L is just basically the L final minus L initial. That is change in L. So this change in L is what we call the extension. Okay, so in this case we want to find the extension. So what are we going to do? So we're going to say that since this is the formula which we have just come up with, we are going to make change in L as a subject of formula. So we're going to cross multiply. So we're going to find that this is going to give us the Young's modulus times change in L times area is going to be equal to the force times this. So I'm going to divide both sides by the Young's modulus times this, then here Young's modulus area. So the extension, which is the change in L, is going to give us force times L initial divided by the Young's modulus times area. So now let's go ahead and plug in the values. We see the extension which we're going to have. Okay, so now what we're going to have there is Young's modulus. The force, we have been told that the force is 25 times, from the question, is 25, as you can see here. Okay, what else? We have the length. The length of the wire, we have been told that it is 1.7. So 1.70, that is the length of the wire. Then I divide this by the Young's modulus. Young's modulus, we have been told that it is 1.6 times 10 raised to the power 11. that is the Young's modulus, times the area. The cross-section area, we have been told that it is 5.74 times 10 raised to the power negative 8. Okay, that is what we have. So let's see, this is supposed to be changed in L and not the Young's modulus. So we have change in L, that is the extension which we want to find. So we are going to see that 25 times 1.70, I'm going to get a 42.5. Okay, 25 times 1.7, yes, I'm getting 42.5. Then down there I'm getting 1.6 exponent 11 times 5.74 exponent neg 8. So down there I'm getting 9,884. So our extension is going to be 42.5 divided by 9184. Okay, this is giving me 0.00, so I can put it in scientific notation, and this is going to give me 4.6. It's going to give me 4.63 times 10 raised to the power negative 3 meters. So this is our extension. Okay, now part 2 is saying the same load is hung from the second wire of the same material. The same material. This wire is twice the length but the same volume. So whenever we're talking about the same volume, even the area is the same. Okay, but the only changes which are going to be there is going to be the length. So this length which we have here, initially this is the length which we have. Now they're saying that now the length is twice as this one which you have, so meaning that is 2 times this one. So now what it means there is that let's continue first with leading the question. This wire is twice the length but the same volume as the first wire. State and explain how the extension of the second wire compares with that of the first one. Now here you can just use, we have come up with this formula. Remember, we have said the extension, which is change in L, is given by the force times L initial divided by the Young's modulus times area. Now, if we increase the length and this one is direct proportion. But what we need to understand is that the length, the extension is direct proportion to what? To the original length, or to the length in short. But the change in L is inverse proportion to the area, meaning that since they are saying that the area, since they are saying that the length has been increased, what it means that even the extension is going to be increased. So that is going to be, so they're saying state and explain how the extension of the second wire compares with that of the first one. Okay, so it's going to increase. Okay, because the length, the original length is direct proportion to the extension. When the length increases, the extension is going to increase as well. Okay, so we have a question which is saying a light spring of an extended length of 14.2 centimeters is suspended vertically from a fixed point as illustrated below. A mass of weight 3.8 Newton is hung from the spring as shown above, or let me say as shown below. The length of the spring is now 16.3 centimeters. An addition force F then extends the spring so that its length becomes 17.8 centimeters. Part 1. Show that the spring constant of the spring is 1.8 Newton per centimeter. Part 2. For the extension of the spring from the length of 16.3 centimeters to a length of 17.8 centimeters, calculate the change in gravitational potential energy of the mass on the spring. Another one is saying that show that the change of elastic potential energy is 0.077 joules. The last one is saying determine the work done by the force F. Okay, so now we start with the first part, where we are being asked to show that the spring constant is 1.8 Newton per centimeter. Okay, so we know that according to Hooke's law, the force, the resultant force, is given by kx. You can say negative kx since we want to find the x, even if you put the negative, but the negative from the resultant force and the negative from this other side, they are going to cancel. Okay, so now we have been given the force already. The force is 3.8 newtons. Okay, so we're going to put 3.8, then has to be equal to k. Then the displacement now, which is x, we have got at equilibrium position, it was 14.2 centimeters. And then after applying this force, the spring extends from 14.2 centimeters to 16.3 centimeters, meaning that to find this x is from this point all the way to where the spring is now. Okay, so it's just a matter of us saying 16.3 minus 14.2. Okay, so if I say 16.3, then I divide, or I say minus 14.2. So this is giving me 2 point. So this is now in centimeters. This is Newton. Okay, this is in centimeters. So I'm going to divide both sides by 2.1 centimeters, 2.1 centimeters. Okay, so my k will be equal to 3.8 Newton divided by 2.1 centimeters. So my k will be equal to it's going to be 3.8 divided by 2.1 is 1.8. So 1.8 is 1.809, so it's same as 1.8 Newton per centimeter. So now show that the spring constant is this. This is how we can show it. As simple as that. We go to the next question. For the extension of the spring from the length of that one, they are saying calculate the change in gravitational potential energy. So now we'll need this k. We can just put it here, 1.8 Newton per this. Now I can find this answer in centimeters, or I say Newton per meter. So how can I find this in Newton per meter? This is going to give me I need first to convert that other one, which is going to be the 2.1, which is going to be, so it's going to be 3.8 divided by, that is going to give us 2.1 exponent negative 2. I want to find k in Newton per meter. Okay, which is giving me 180. So it's same as 181 Newton per meter. Okay, that is very, very important as well. Okay, because there's a question which we need to solve and we need to use that k. Now the k has to be in Newton per meter. Okay, so there we go. Now we go to part 2, which is saying for the extension of the spring from length of 16.3 centimeters to length 17.8 centimeters, calculate the change in gravitational potential energy. So they are not asking about the change in elastic potential energy, no, but gravitational potential energy. Gravitational potential energy is always given by mgh. Okay, so mg in this case, it is the weight of this block, and the weight of this block, we have been told that it is 38. Okay, so we are going to say that this is 38 now times the h, the height. Now this height, the height which we are going to get, we need to understand there. Okay, so the height they are asking to say from 16.3 all the way to 17.8, we are going to say 17.8 minus this for us to get the what, the height. Okay, so if I do that, what I'm getting, we are getting 1.5. Now this 1.5 we need to convert it into meters. Okay, so 1.5 I divide it by 100. It's going to be 0.015. So this is going to be 0.015. So our gravitational potential energy is going to be uh, is 5.7 times 10 raised to the power negative what? Negative 2 joules. This is the same as 0.00. Yeah, it's the same as we say 0.0. If you don't want to put your answer in scientific notation, you can say 0.015 times 38. This is 3.8, by the way. Yeah, 3.8. So it's supposed to be 3.8. So it's 0.0. It's the same as we can say 0.057 joules. So that is our gravitational potential energy. Okay. Now our next question is saying we need to show that the change in elastic potential energy is given by 0.07 joules. Now what we need to understand here is let's first put this here. Okay, so the gravitational potential energy, we have said that this is 0.057 joules. So to find the change in elastic potential energy, what we have to do is elastic potential energy is given by this. But what we need to understand is that we have got the change in x. The change in x from here all the way to here, we have another change in x. Again, from there all the way to there, there is also another change in x. That is what we need to know. Okay, so what we're going to do there is I'm going to say we are going to have x1. Okay, now this x1 is going to be 16.3 minus 14.2, which is going to give me 2.1 centimeters. Now to convert this one into meters is same as just saying times 2 to the power negative 2, just like this. Then x2 is going to be 17.8 minus 14.2. So this is going to give me 3.6. So now this is centimeters. To convert it into meters, I'm going to say times 10 raised to the power negative 2. But if you want, you can just say 2.1 times divided by 100, which is just the same thing. Okay. So now what I'm going to do now here is elastic potential energy is going to be half k. This is going to be 2x2 minus x1. Then I square it. Okay, squaring this is the same as I even square direct. It's the same as I say elastic potential energy. Okay, since this is square, this is supposed to be squared, so it's going to be this x2 squared minus x this. Okay, so what I'm going to do now is this is what I wanted to. So this is the k. So the k which we have is 181. Then here we have 3.6 times 10 raised to the power negative 2. Now we square it, minus 2.1 times 10 raised to the power negative 2, and then I square it. So this is going, if you get your calculator, this is going to give us half times 181 is going to give us 90.5. Then inside there we're going to get 0.000855. You can also use your calculator if you'll be able to get the same answer. Okay, now from there, what else? From there now, what we need to understand is that we get our calculator and then we see what we're going to get. So the answer which we're going to have is 0.077 joules. So this is how we can show that the elastic potential energy is given by 0.077 joules. Last question is saying determine the work done by the force. Okay, by the force F. So to determine this work done by the force, it's the same as we have found. Remember, we have found the what? This one. So this one, it is the same as the force which is it is the same as the work done, which was done by what? The force, which is 3.8. Now to find this, we need to find the change in what? We're going to say this. Okay, we know that the work done is force. Work is given by force. It's going to be this times what? X. But if you are trying to derive this formula, you are going to discover that this formula is going to take you back to this. Now, what I want us to understand is that here we have two things. We have got the work done by the gravitational force and the work done by the what? The one which we have found here, the elastic potential energy. Okay. So to find this, what we have to do is we're going to say that the work done by the force is going to be the work done by F. So it's going to be this, the potential elastic potential energy minus the gravitational potential energy. That's all. Okay, so this is going to be like this. It's going to be 0.077 minus 0.057. So that will be the work done by the force, because we know that this 0.05, it is the work done by the 3.8. So if I do minus the work done by overall, which I have here, meaning that is going to be the work done by the what? By the force F. So 0.077 minus 0.057. Okay, so I'm getting 0.02. 0.02 joules. So that is the work done by the what? By the F. So this is how you get to answer such kind of question. Okay, so we have the next question under simple harmonic motion. Specifically, this question is under elastic potential energy. So a 0.250 kg block attached to a light spring oscillate on a frictionless horizontal table. The oscillation amplitude is 0.125 meters and the block moves at 3.00 meters per second as it passes through the equilibrium at x is equal to 0. Find the spring constant K, that is part 1. Part 2, which is part B, calculate the total energy of the block's spring system. Part C, find the block speed when x is equal to a over 2. Okay, so now what we need to understand first, we need to know the conservation of energy in elastic potential. Okay, in elastic potential energy, how do we tend to calculate the velocity? How do we tend to calculate the constant K, which is the spring constant? Okay, so now let's say we have a spring. Here is our spring. Now we are trying to stretch this spring all the way to this point. So we know that we are going to have the mass, which is going to be here. Let's say that this point is our equilibrium. So at equilibrium, x is always 0. Okay, so now if x is equal to 0, we know that at this point, that's where we are going to have the maximum velocity. Okay, so here we are going to have the maximum velocity, Vmax. If we have the maximum velocity, we expect to have the kinetic energy. The kinetic energy, that's where it's going to be at its maximum. The potential energy, since we know that the potential energy, the elastic potential energy is half kx squared. So if x is 0, the potential energy is 0. Now, the moment you stretch this spring, at this point we expect to have the maximum acceleration. So if you have the maximum acceleration, the acceleration is going to be, the velocity is going to be 0. If the velocity is 0, kinetic energy is what? Is 0. And at the same point, this is going to be, x will be equal to a. When you have stretched the spring at when you have stretched the spring to its maximum position, x is equal to m. What it means there is that x is going to be equal to the amplitude. So if x is at its maximum position, meaning that we expect to have the potential energy. So at this point we expect to have what? The maximum potential energy. Okay, so what we have here, this is the same thing which we're going to have at this point. At this point, we expect to have the velocity to be 0, kinetic energy to be 0, potential energy to be at its maximum position, acceleration to be at its maximum uh, point when you are compressing the spring. Okay. Now, what we need to understand here is whenever we are trying to come up with the formulas, we start from conservation of energy, where we know that mechanical energy is the sum of the potential energy, which is the elastic potential energy, plus the kinetic energy. At this point, we can't add the gravitational potential energy because we only have the elastic potential energy. Okay? So mechanical energy is given by half Ka squared. Elastic potential energy is given by half Kx squared. Then kinetic energy is always half mv squared. Now, why are we putting A instead of X here? Since we are saying that mechanical energy is the sum of the elastic potential energy and kinetic energy, meaning that at that point it has reached at its maximum position. That's why I'm using M. So mechanical energy is given by half Ka squared, where A is the amplitude. Okay, so now from here, as long as the question is saying it has reached at its equilibrium where X is 0, meaning we don't expect to have this part is going to be 0. Okay, so this is going to be cancelled. We are going to have half Ka squared half mv squared. So we are trying to make K as a subject of formula. What are we going to do? I can do times 2 everywhere. So if I do times 2, I'm going to get K a squared is going to be equal to mv squared. So I'm trying to make K as a subject of formula. Here I'm going to divide both sides by a squared. Here also a squared. So what I'm going to have now is for me to find the spring constant, since I have the velocity, I have the mass, I also have the amplitude. So the K will be equal to the mass times v squared, everything divided by a squared. So it's just a matter of us now plugging in the values. We see the value of K. So K will be equal to, the mass is 0.25 times the velocity is 3.00. Now we need to square it. The amplitude is 0.125. Now we square it. So what will be the value of K? So if we do 0.250 times 3 squared, I divide this by 0.125, I square it. So I'm getting my K as 144 Newton per meter. So that is the value of K. Okay. So now, if this is the value of K, we can put it somewhere because we will need this. So K, we are saying that is 144 Newton per meter. Okay. What else now? Part B is saying calculate the total energy of the block spring constant. So now here is just a matter of us to calculate the total energy. It's just a matter of finding the what? The mechanical energy. And we are saying that mechanical energy is given by half Ks squared. The total energy, it is the addition of the kinetic energy and elastic potential energy, which is the same as the mechanical energy. Okay, so since we have found the K to be 144, the A is 0.125. Now we square it. So what will be our total energy? 0.5. 1 over 2 is 0.5 times 144, then times 0.125. I square it. I'm getting 1.125 joules. So that is the total energy of the block spring system. Okay. So we go to part C, where it's saying find the block speed when x is equal to a over 2. So here, what I want us to do is let's just get rid of this, and then we see the formula. Now, whenever you are trying to calculate the speed, we need to come from here, the elastic potential energy plus the kinetic energy. So we know that this is half ka squared half kx squared plus, then you have half mv squared. Now we are trying to find uh, the speed. Okay, so now if we're trying to find the speed, we can see that from here we can shift this to the other side, which is going to be half ka squared minus half kx squared to be equal to half mv squared. Our goal is to find the v, so I can do times 2 everywhere so that I get rid of half. So this is going to be ka squared minus kx squared to be equal to mv squared. Okay, what else? From here now, I want to make v as a subject of formula, but from here I can factor out a k. So k will be open brackets a squared minus x squared, then this has to be equal to mv squared. But remember, the question is saying where there is x, we put a over 2. So what I'm squared was equal to k, then a squared minus x squared over m. Now if I get the square root both sides, okay, this is going to give me plus or minus, it's going to give me this over m. But I know that this is the same as, I can write it in this form. I can say k over m and then times, I need to remove that square root. This is going to be a minus x, which is just the same thing. Okay, so now I want us to find x. So it's going to be a over 2. X will be equal to, a is 0.125, everything divided by 2. X will be equal to, so 0.125 divided by 2. Okay, I'm getting 0.0625. So this is what I'm going to put there. Okay, so our v will be equal to plus or minus the square root of k. So k, now we know that k is 144, the mass is 0.250, and then times, now a, we know that a is 0.125 minus 0.0625. okay, so v plus or minus, what are we going to have? We're going to have 144 divided by 0. Or we can first find this, so that okay, so it's going to be 0.250, then I get the square root. This is giving me a 24. Okay, a 24. So this times, what is 0.125 minus 0.0625? This is giving me 0.0625. So I do times 24, which is giving me 1.5. So that is our velocity. So our v will be equal to plus or minus 1.5 meters per second. So that is it for part C. But you can also use another method where you just say the potential energy is going to be equal to the kinetic energy. Okay, then you'll be able to get the same answer.